So here is a schematic diagram of how we can study the energy budget at the top of the atmosphere. So the total energy budget analysis can be carried out as per shown here. So how do we do it is like we can actually calculate the high latitude dynamics. Once we know the high latitude dynamics, from that we can actually measure the surface temperature changes. So from that we can actually use the equations to find out what is the total energy budget. Again, one is the high latitude dynamics, but this is questionable at very high latitude simply because due to the presence of clouds and other things, this is going to be a little bit tricky to carry out. And of course, if we are going to study the surface temperature from the high latitude dynamics, then static stability complicates the entire analysis. And when we talk about the tropical dynamics relies on the satellite data. So if you have a reliable satellite data, then we can actually find out what is the tropical dynamics, and the effects due to moist convection also can be measured. Then we can easily find out what is the surface temperature change. Once we know the surface temperature change, then we can use it for the total energy budget analysis. And the next one is the surface energy budget analysis. That means it is at the earth surface. So this actually simplifies the entire climate process. We are making lots of assumptions here. So this actually simplifies our analysis. And this surface energy budget analysis can be directly related to the surface temperature changes. And we also know what are the feedback mechanisms that are happening. And once we capture the upper and lower tropospheric process, then it will be easy for us to identify what is the feedback mechanism that is happening. And this feedback mechanism also has different feedback magnitude with respect to the total energy budget. And once we know the feedback mechanism, then we can actually make a model which is consistent and which can be used for evaluation. The only thing is, it is very, very crucial for once we know the feedback mechanism, then we can actually make a better model. So this is a very, very important thing, that we need to know what is the feedback mechanism. And once we can create the model, then we can actually understand the climate behavior. So we have to only find out, is there any discrepancies. Once we know there are some discrepancies, we have to use those parameters in the calculation. Then we can understand the entire climate behavior. Once we know the entire climate behavior, that is the major thing we are actually going to do with the help of total energy budget analysis. So once we know the total energy budget, then we can actually understand the climate behavior in a much better way. So what are the different types of transpiration? We have three major types. One is the potential evapotranspiration. So this is sufficient when the sufficient moisture is freely available to completely meet the needs of vegetation, fully covering that area. That results in the evapotranspiration, and this is what is called the potential evapotranspiration. Here the assumption is it has to cover the full area. So that's the only thing we have to know. So the full area, if we can cover, that is what is the potential. That means how much it can actually happen. But actually, is it happening? That is a different question. That we will be answering in the next two cases. So in the potential evapotranspiration means all 100% that is possible. So the loss of water due to evaporation and loss and plant transpiration, so all are included here. When we talk about referential evapotranspiration, this is the evapotranspiration rate from a reference surface, not short of water. That means there should be plenty of water there. Then this is called the reference evapotranspiration. And that means we are assuming that 100% evapotranspiration is possible in this particular area. So here we will define a particular area. The reference surface is a hypothetical grass reference crop with an assumed crop height of 0.12 meters and a fixed surface resistance of 70 seconds per meter and an albedo of 0.23. And then we have the actual evapotranspiration. So this is the real evapotranspiration occurring in a specific situation in the field. So one is the potential, how much is possible, and we have a reference. When we have these two things, we can actually measure what is the actual. So there is a simple model for the evapotranspiration measurement. In the Arctic region underlying by permafrost, Percolation into groundwater and soil water storage is severely limited. So that means water cannot easily go through that because it is both ice and soil. So that is what is permafrost. So percolation is not possible. The groundwater cannot easily pass through. And due to this, we can completely eliminate this from the water balance for seasonal estimates. So that means we can assume that no water will seep through. That's it. That's as simple as that. Then evapotranspiration from the waste watershed isolated from groundwater flow is easily calculated from this one. Evapotranspiration is equal to P minus Q minus ds. What is P? P is precipitation, that is given in millimeters. Q is the surface runoff, that is again given in millimeter. ds is the change in the surface under soil water storage. So from this we can measure what is the evapotranspiration happening in the Arctic. So there are various nonlinear controls on evapotranspiration, that is the variation in the near surface soil moisture and the atmospheric vapor pressure deficits have nonlinear effect on the midday evapotranspiration rate. So these are all some of the parameters we have to consider while you are calculating the evapotranspiration in the Arctic region. Then dry soils increase the bulk surface resistance. Wet soils favored the ground heat flux and therefore limited the energy available to sensible and latent heat flux. So these are some of the things, like if it is a dry soil, then we can say it is water limited, and if it is a wet soil, we can say it is energy limited. And here the midday evapotranspiration was suppressed from both the dry and wet soil, but through different mechanisms. So they both affect, but they affect through different mechanisms. Then various controlling factors at the midday evapotranspirations are given here. So we have to account all these things when we do the calculation for evapotranspiration. And what are the factors that specifically affect the Arctic region? So here the transpiration rates are greatly differ between drier and the warmer sampling period because of the wetter and the colder sampling period, because the area is very cold. So that's the reason it may hold more moisture. And evapotranspiration is highest in the centers of the low centered ungraded ice wedge polygons and lowest in the low centered degraded polygon. So that means we have seen the thermocrust lakes that are being formed. So the evaporation at the ridges or at the end of that water lake and the middle of the water lake are going to be different. So that is what given here. Then again, we can also say that the polygon rims reveal that evapotranspiration was highest in the mixed polygons and lowest in the low and high centered degraded polygons. If the thickness of the water layer is very low, that means it actually reaches the soil very quickly. So sunlight can heat very quickly there. So the albedo is going to be much less. In other words, like it is going to get heated up very quickly. When it heats up very quickly, what does it mean? It will actually lead to more evaporation. So that is what it is given here. Evapotranspiration is going to be very high. And ET changes are coupled to the landscape alterations such as permafrost changes, vegetation shift, fires and lakes and reservoir changes. So these are all possible in the Arctic region. And the only thing is the evapotranspiration cannot be related with the certainty to the season length, because we cannot say if summer is very long then evapotranspiration is going to be high, or if winter is long then it is going to be less. So these kind of comments we cannot actually make. So here are some of the pictures given here. The lichen dominate the dry areas. So here we can see the dry areas. Lichens actually dominate these dry areas, and the mosses dominate the wetter areas in the pond. So these are all the two major algae type materials which are seen in the Arctic region. And let us look at the changes in the evapotranspiration. So evaporation and evapotranspiration are among the primary mechanism of summer energy dissipation. So here it is greatest in the early summer, immediately following the spring snow melt during the period of maximum incoming radiation, but not necessarily the maximum air or soil temperature, and decreases throughout the summer. So this is what the transpiration reduces. The evapotranspiration also decreases as the latitude increases, and the losses from the lakes are greater than evapotranspiration losses from an equivalent terrestrial area. So this is the major difference between the terrestrial and the Arctic region. The permafrost dominated basin tend to have lower evapotranspiration than those with the less permafrost. So the permafrost is more means that they will have lower evapotranspiration. That means less moisture will be given out from that soil. Temporarily, the annual evapotranspiration in the permafrost dominated basins have increased faster than in the less permafrost developed basins over the past 4 decades. So these are all the observations which people had made. And how the evapotranspiration is measured? This is measured using a lysimeter. So, because making this direct measurement, especially in the Arctic region, is a very difficult task. The potential evapotranspiration and the class A pan evaporation measurement can be used to estimate the actual evapotranspiration. So here we use the models to figure it out how much actually would have happened. And of course, micrometeorological based methods such as Bowen ratio energy balance, the eddy covariance technique, and the physically based methods like Penman-Montieth equation are used for the calculation of ET by forest vegetation. And the tundra and the wetland have a high surface resistance, so which are less sensitive to vapor pressure deficits. So the variation in surface resistance within and between the different vegetation types will play a very significant role in the energy exchange between the terrestrial ecosystem and the atmosphere. In other words, Arctic is highly affected by the presence of tundra and wetlands. How ET model can be developed and studied? Here are some of the examples. The types of ET models development is given here. One is a machine learning model, land surface model, data assimilation model, and satellite remote sensing models. If someone is interested to know, they can read some of the papers given here. The next one is global land evaporation Amsterdam model. So this is basically a satellite remote sensing based set of algorithms. They are dedicated to the estimation of evaporation and soil moisture at the global scale, and the GLEAM is a simulation as E as a summation of its constituents. That means transpiration, bare soil evaporation, open water evaporation, snow sublimation, and interception loss. Then when we talk about Penman-Montieth model, and there is also Priestley-Taylor model, these are other models which are used to calculate the evapotranspiration.